Hi guys, this is Jonathan Lambert with Maths and Stats, and in this video, another video in our series of videos dealing with calculus and limits, and specifically epsilon delta proofs, we'd like to use the definition of a limit, the epsilon delta definition of a limit, to show that the limit of this linear function here, so that the limit of 7x minus 2 as x tends to 4 is in fact equal to 26. But before we get there, let's just recall the definition of a limit. So let's just recall our definition of a limit. So it's, I suppose, given a function f, okay, we say that the limit of f as x tends to a specific value exists, given an epsilon greater than 0. There needs to exist some delta greater than 0, such that for each and every x that satisfying the condition, the premise that 0 is less than the absolute value of x minus a is less than delta, that needs to imply that the absolute value of f of x minus L is less than epsilon. Okay? And so just keep in mind here that a is what x is tending to. Okay? F of x is the function, and L is the limit that the function is actually is equal to as x tends to the value a. So in our case, what we have is that if we're given any epsilon greater than 0, we need to find a delta greater than 0, such that for each and every x in this particular region here, for each and every x satisfying that 0 is less than x minus a, that's where the limit is, that's where the that's where our indeterminate is tending to. X is tending to 4, so x minus 4 has to be less than delta. So for all x in here, after being given this epsilon, we should be able to find a delta such that all x in here implies that f of x, which is 7x minus 2, that f of x minus L, which is 26, has to be less than that particular epsilon that was provided. Okay. So how are we going to go about this? Well, what we need to do is we need to find this particular delta. Okay. Now, how the hell are we going to do this? Well, why don't we do something? Why don't we just go looking for the delta? We need to satisfy this particular implication. Okay? This premise has satisfied this conclusion. So let's consider the conclusion, okay? Because that's where we need to get to. Okay, so let's consider the conclusion, and let's see, can we find this particular interval hidden within this particular conclusion? So let's consider the conclusion. So let's consider the conclusion. Right? And the conclusion is of the form, don't forget, f of x minus L is less than epsilon. So we're going to just consider this thing here. So what does this tell us? This tells us, so 7x minus 2, the absolute value of 7x minus 2 minus 26, as the function minus its limit, okay, has to be less than epsilon. Okay? Well, let's get rid of the brackets here. What does this tell us? Well, therefore, we have that 7x minus 2 minus 26 gives us minus 28. That's the absolute value of that has to be less than epsilon. Okay? Now, what we'd like to do is that we'd like to let's say reduce this particular statement. We'd like to reduce this statement down so that we get something like this, that we get inside the absolute value, that we get the x minus a. Okay, because we know that this absolute value is less than epsilon. So let's try to reduce this down to see what happens if we reduce it down to x minus 4. We can see that there's a common 7 across here. So this is the 7 times x minus 4. 4 sevens is 28. Must be less than epsilon. Okay, wow, now we're nearly there. Okay, we nearly got x minus 4. So 7 times, the absolute value of 7 times x minus 4 is the same as the absolute value of 7 times the absolute value of x minus 4. Must be less than epsilon.